All right, so last time we finished off by starting the second part of vectors, which in your packet is section 5.4. If you're looking in your book, everything this week is section 8.5. Okay? So we had gone through all these formulas. Okay? And the nice thing about them is it gives us a way to add, subtract, and scale vectors without sketching. Okay? That's how we learned to do it before we had these formulas. Okay? So now we can just use numbers and we don't have to worry about actually drawing things out. Okay? So we'll try like an example of each one of those things. Okay? And you already did a little bit of this in the homework. Okay, so the first operation they want us to do is take vectors v and w and add them. Okay, what we'll do is we'll write our answer in unit vector notation and algebraic notation. Okay, we'll do it both ways. All right, so when you add v and w, what's the horizontal component when you add those up? How many? Okay, so the individual components are 2i and 3i, and then when you add them, you would get 5i. And how about when you add up the vertical components in v and w? Negative j. Okay, so that's how you can write your answer in algebraic form. I'm sorry, unit vector form. And then how about that way? How would you write it? 5, negative 1. You don't need the negative 1 when it's in the unit vector form. You can put the 1 in front of j if you want, but you have to put it when it's in the other form. Okay. Any questions on that? So if we were going to add these the old way, we would have had to take two vectors and line them up, the end of one and the beginning of the other, and then we'd have to draw the diagonal to get the answer. Okay? But now we don't have to do that. Okay, we just use numbers. Okay, how about v minus w? Amanda, what's going to be the I component when I do v minus w? How much?
Would it be like just I?
Not I, you're close. Negative I. Okay, because it's 2 minus 3. If I did w minus v, then it would be I. But this is v minus w. So negative I. And Molly, how about the j component? Yeah, because it's 3 minus negative 4. So 7j. Or if you wanted to write it with the angle brackets, it's negative 1, 7. Any question on that one? So those are the two operations. To do them, you need two vectors. This one you don't. This is just a single vector. We don't need w at all. I'm just going to take vector v. And what do we call this when you put the number in front of a vector? It's a scalar. We're scaling the vector. It's a scalar product. Okay, we'll get into other kinds of products later today, like a vector times a vector. Okay, but not this one. So what do you get if you take the vector v and triple it? 6i and 9j. So 6i plus 9j. Okay, and the last one, we did a couple of these in the homework, finding the magnitude. And again, when you find the magnitude, basically you're just doing what? Yeah, you're just doing the Pythagorean theorem. You're just drawing the two sides of a triangle, or the numbers they give you in the vector, and it's like you're finding the hypotenuse. Okay, so we've got the vector 2, 3. Yeah, so it would be, just to show it out, it would be 2 squared plus 3 squared, which gives me 4 plus 9, or the square root of 13. Okay, and as always, if you can reduce that, you go ahead and reduce it. If you can't, you just leave it like that. Okay, so any questions on adding, subtracting, scaling, or finding the magnitude? Okay, which answer there is different than all the other answers? D, what's different about it? So what does that mean? There's no I's and J's. Okay. It is like the hypotenuse of a triangle. What else? What's different about that answer than the other three?
The other ones have two numbers, that only is one.
Okay. How about tying it into the thing that we're studying this week? Yeah?
It doesn't have a direction.
Why not?
It's just magnitude.
Yeah, it's just a number. Yeah, that's all it is. It's just a number. Every other answer is a vector. A, B, and C are vector answers. D is a number answer. Okay? If you're trying to classify what kind of answer you have. All right, so remember we said yesterday that if the length of a vector is equal to 1, then it's a unit vector. So sometimes what we might have is, let's pretend that vector in red is 1 unit, and the vector in black is longer than that. So what we might want to do is change the length of it so that we can turn it into a vector that's 1 unit long, but keep it pointing in the same direction, just like I have here. What do you call that if you take a vector and shorten it or lengthen it? You scale it. Okay? So if we have a vector and we want to turn it into a vector 1 unit long without changing the direction, we can scale it. So we're going to look at how do we find a unit vector. Let's say this vector in black was 5 units long. What would you have to scale it by to turn it into a unit vector? You'd have to scale it by 1/5. Okay? If it was 8 units long, you would scale it by 1/8. Okay? You basically scale it by 1 over the magnitude. So what if it was x units long? What would you scale it by? Not 1x. 1 divided by x, 1 over x. So the idea is all you have to do is take a vector and divide it by its length. Okay? If it's 10 units long and you divide it by 10, it becomes 1. If it's 8 units long and you divide it by 8, it becomes 1. Okay? So we're finding a new vector that points in the same direction, but it's only 1 unit long. Okay? And the idea is you take the vector and divide it by its length. Or some of you said to do this. Take the vector and multiply by 1 over its length. That's the same thing. So really we're doing a scalar product here. So anytime you want to find a unit vector, the first step is to find the length. If it already is 1 unit long, you don't have to do anything. If it's not 1 unit long, follow the formula. Okay. Any questions on how we came up with that formula? All right, so not something we really do a lot, but we'll just practice one problem with finding a unit vector, and then we'll move on to our 2-word problems. Okay, so I'm given the vector 3i minus 4j, and I want to turn that into a unit vector. So to check if it already is a unit vector, what should I do first? Yeah, let's find the magnitude of it. If it already is 1, then we're all set. If it's not, then we'll plug it into the formula and turn it into a unit vector by scaling it. We might have to scale it shorter. Or if it's too short, we might have to take the vector and make it longer. Okay? So what's the magnitude of the vector? 5. Yes. 9 plus 16. Add them up, you get 25, and then take the square root. So is the vector we were given a unit vector? No. So we're going to take the vector that we were given, and what am I going to do, or what am I going to scale it by? 1/5, which is the same as dividing each component by 5. So I'm going to do 1/5 times vector v. And it's going to turn it into a vector that points exactly the same way. We're just going to scale it down to be 1 unit long. So what would be my answer? Yep.
3/5 side minus 4/5.
3/5 side minus 4/5 j. Yep. Or if you wanted to do it with the brackets, it's 3/5 comma negative 4/5 in the brackets. That's it. That's all you have to do to find a unit vector. And you could check, make sure the length is 1. If you square the first fraction, you get 9/25. Square the second one, you get 16/25. And what do you get if you add those up? 1. You get 1, and then you take the square root of it, which is 1. So we just check the length of it, and it is 1. Okay. So any questions on how to find a unit vector if you're given a vector? Okay, as long as you're given a vector that's not the 0 vector. You've got to be given a vector that actually has magnitude and direction. All right, so the last two things in this part of the section are the word problems. Okay, the first one's pretty straightforward. Okay, it's called a velocity vector. So we're going to do one example with a velocity vector, and then the next example we're going to do is with force vectors. Okay, so a velocity vector basically describes the speed and direction of an object. So when you throw an object at an angle, like if I were to throw an object like towards the top of the door from here, what two directions is the object moving in? Yeah, it has two components to it, right? It's moving, in this case, up, and it's moving to your right, okay, towards the door. Right, so that's the idea we have to kind of think about when we want to write something as a velocity vector. There's a horizontal component, and there's a vertical component to the velocity. Okay, so let's pretend that's the vector that represents how I am throwing an object. Okay, and for our purposes, we're going to pretend that we're just throwing it. Obviously, it would start to curve back down at some point, but we'll just, to make it simpler, we'll just pretend that it just keeps going on that path. All right, so the bottom line represents the horizon. Okay, that's like the horizontal, and this is the angle above the ground that you're throwing the object at. Okay, in order to separate this vector into its components, what do I need to do? Visually, not calculations yet. Yeah, we need to draw a right triangle. So all I need is a vertical line. Just put that in right there. And now I can separate that vector into its components. That's the horizontal, and that's the vertical component. Now, I want to figure out what each one of those are kind of in relation to that angle. Okay, let's temporarily, we can call this x and y, but we're going to figure out what x and y are in terms of my vector and the angle I throw the object at. Okay, so let's start with x. Or we might need to go one step back from that. Let's start with what trig function we need to use to figure out x. Cosine. And what would the cosine of theta equal? Okay. Yeah, the magnitude of v. So technically here, if these are all vectors, it's really the magnitude of x, but just to simplify it, I'm just calling it x over the magnitude of v, because the magnitude is the actual length of the side. And now how would I get x by itself? Multiplied by the magnitude of v. So there's a formula for x. And now, without setting the whole thing up again, anybody think they could tell me the formula for y? Yeah, it would be magnitude of v sine theta. Okay, so basically what we're going to do is take this. X is your horizontal component. Y is your vertical component. And substitute in those two expressions into that formula. This is a vector this is unit vector form. I'm going to turn it into a velocity vector. And I'm going to get rid of the x and the y. And all I'm going to have is theta with a trig function and magnitude of v. Okay, so we'll substitute those two boxes in for exactly what I just wrote. And I think I thought I did that. No, I'll just do it out right here. So we got magnitude of v, cosine theta, and that's the I component, plus magnitude of v, sine theta, and that's the j component. Now, what does each term have in common there? They both have a magnitude of v in front of them. So what can I do with that magnitude of v? I can factor it out. And that's the final version of the formula I have on the other page. It's the magnitude of v factored out from that. Where is it? Right here. So magnitude of v factored out. And I called my angle theta. You can call it alpha. Whatever Greek letter you want. If you want to just stick with theta, because that's what we wrote, that's fine. So it's cosine theta I plus sine theta j in parentheses, and then the magnitude has been factored out. Okay, and that's the formula for a velocity vector. You just fill in your magnitude. That's basically how fast you're throwing the object. Fill in the angle. That's the angle that you throw the object at. Okay, it's important that I added those bars because v is not the initial velocity. The magnitude of v is the initial velocity. Okay, and technically v is a vector. So to make it clear, either take V and make it look bold, or put the arrow on top of it. I guess since I used I and J and made them bold, to be consistent, I should just make that look bold. Either way. Okay, so any questions on the formula for a velocity vector? Okay, what's a little more important here is just to kind of understand that cosine generally deals with the horizontal component of something, and sine deals with the vertical component of something. So when we do forces next, the same idea is going to happen. Cosine is always the horizontal, sine is always the vertical. If you forget, you can always just draw your triangle and do opposite, adjacent, and that stuff. All right, so suppose that we're throwing an object at 50 miles an hour at an angle of 30 degrees. I want to find the velocity vector. So we'll do that first. Then I want to write the answer in unit vector form. So that means we actually have to do out the cosine of the angle and the sine of the angle, do it all out. And then once I get my final answer, I want to explain what each component in the answer means. Okay, so let's start with our velocity vector. What's the initial speed? Well, once we release it from our hand, 50 miles an hour. So 50 miles an hour times, and then what trig function comes next? Cosine of, what's my angle? 30. And cosine is which component? That's the I, or the horizontal. Plus sine 30 J. Okay. And since they asked for the answer in unit vector form, we have to distribute and do this out. So what would be the calculation I have to do to get the horizontal component? $50 times cosine 30. So we'll just type that in. Make sure you are in degrees. Okay, so we got 50 cosine 30, which is 43.3 I, plus, what's the sine of 30? 0.5. So 50 times 0.5 is 25. Okay. So there's the velocity vector in unit vector notation. And the last thing it says is to explain the meaning of each component. So what's the 43.3 mean in terms of this object actually traveling? What is that? Yeah?
So far, what horizontal?
So you're saying this is a distance?
I mean, say what's the speed?
The speed it went horizontally, yes. So it's not how far it went, but it is the speed horizontally. So in other words, if you were to throw this object and somebody was standing directly in front of the object, it was coming right at them, and you pointed a radar gun at the object, it would say the object is coming at them at 43.3 miles per hour.
So vertically?
And the 25 is the speed vertically. So if somebody was directly above the object, the ball would be coming up at them at 25 miles per hour. It would kind of be doing an arc, but it would be going up at 25 miles per hour and forward at 43. One of those speeds, if you ignore air friction, would never change. So ignoring air friction, which speed stays the same for this entire problem? Yeah? The horizontal speed. Gravity has zero effect on horizontal speed. The only thing gravity is going to affect is the vertical speed. That's why when you release the object, it goes up and it comes back down. Okay, because eventually it's going to reach a point where it's going 0 miles an hour vertically, and then it's going to start coming back down. Okay, but that 43.3 doesn't change at all. With air friction, it changes a little bit. So knowing these two speeds, we could find out all kinds of things. We could figure out how far the ball is going to go. But in order to know that, we'd have to know how long the ball is in the air for. And if you tell me you're throwing an object up at 25 miles an hour, we could figure out exactly how long it's in the air for, due to gravity and things like that. And then if we know how long it's in the air for, we could just use distance equals rate times time to figure out how far the object goes. Right? So there's lots of different things you could figure out now that you have this. But we don't really get into, it's called Newtonian mechanics, the physics of that. But we just find that vector. Any questions? All right, so the last example in this section has to do with a force, or several force vectors. And it's kind of, this problem is about static equilibrium. Any thoughts on what that might mean? Something static and something in equilibrium, kind of putting those two ideas together? Yeah?
It's balanced while not in motion.
Yeah, basically all the forces acting on the object are balanced. Nothing is going to be moving. Okay, so basically everything on this table is in static equilibrium. The book has a certain force to it pushing down on the table, but the table is also pushing back up on it. That's why it's not falling. It's balanced. So we have to think two-dimensionally when we do this. We're not really thinking three-dimensionally. We're really thinking two-dimensionally to figure out the forces that are acting on an object. Like if you had a traffic light hanging from two cables, what direction would the traffic light want to travel in if you were to cut one of the cables? How would it travel? Can you kind of break it up into components for me?
Well, if you got the left wire, one goes to the right.
Okay, it would swing to the right. Any other direction at the same time? Down. Yeah, it would travel in two directions. So if you had something, like an object here suspended from two cables, if you cut one of them, it would swing down and to the right or down and to the left. Okay? We're not going to worry about swinging forward and backward, just thinking two-dimensionally. Okay, so the idea here is I want to find the tension in each cable. Have you done that before?
Yeah,
So if the cables were, the simplest case would be if you just had two cables vertical in the object, evenly spaced, then the tension would be half in each cable. But when you have cables that are different lengths, the tension isn't necessarily the same. And the tension can be even more than the tension in the cables can be more than the actual weight. If you think about like a tug of war rope, right? Maybe the rope, it's usually a pretty heavy rope. Maybe the rope weighs 30 pounds. But the tension in the rope can be a lot more than that. If you've got 50 people on each side pulling, the tension in the rope could be thousands of pounds of tension, even though the rope doesn't weigh thousands of pounds. It's because there's a lot of tension on it. All right, so the tension in each cable here doesn't necessarily have to add up to 1,200 pounds. It might add up to more than that because the cables are pulling against each other, and that's what's balancing it for moving. Right? Right, so what we'll do is we'll give names to the tension in each cable. We could call that T1 and T2. So the first thing I want to do is just kind of set up the equations, not necessarily the actual numbers in this problem, just the concept or the idea. So this object isn't swinging. Right? It's perfectly stable. So what does that mean about the forces? Yeah? All right, they're all balanced. Everything's in static equilibrium. So specifically, what does that mean? Which forces are in static equilibrium? Thinking two-dimensionally. Left and right. So the force pulling the object left and the force pulling it right. That's not really an equation, that's just an idea. We need to figure out what is the force left and right based on our diagram. And what else? Yeah?
Force is going up, force is going down.
Yeah, the force pulling up and the force pulling down. Again, that's just more of a concept. We haven't really plugged numbers in. But those are the equations you need to set up. And that's what's going to lead to a system. So we have to figure out these four things. So I'm just going to move it down a little bit. So think of these as vectors, right? Kind of pulling the way I just drew the arrows. What do you think we want to do with these vectors? Yeah? Yeah, we want to find the components. And how, visually, how do we do that? Yeah, we're going to make some right triangles. Okay, so I need a horizontal, and then I need two vertical lines, segments. Yeah, put one here and one about there. Okay, so now I just created two triangles. And we've separated, once I draw it out, we've separated these vectors into components. What's that force? That's a left force. And why don't we call it, well, we could call it force, we could call it the force left, but let's, because we're usually used to using x's and y's, and I think that'll, when we start to do the trig part, x and y will help you remember which direction is which. Let's call this x1. Okay. And we'll plug that in for force left in a second. What about this one? We'll call that x2. And what about that one? That's y1. And this one? y2. So now I can change these equations a little bit. I still don't have too many numbers to fill in, but what is the force left in that diagram? Yeah, so this is going to turn into x1 equals x2. We still have to figure out what x1 and x2 are based on the angles here. Okay? But that's basically what we did in the last problem, using sines and cosines to break this apart. And what's the force up? And y2. Both y1 and y2 are pulling up. And what's the force down? 1,200. So far, that's the only number we have. The force down is 1,200 pounds. All right, so now we're going to set up four expressions to figure out what is x1, x2, y1, and y2. But to do that, I need to know a little bit more about the triangles I just drew. I don't have anything labeled inside these triangles. Okay. Is there anything that I could label inside the triangle on the left? Yeah. We could do the triangle on the left, and we're going to have to do the one on the right in a second as well.
Don't you do, because, wait, do we know that the folded line is a straight line?
We know all those lines are parallel except for the two cables. Everything there is parallel. Yep.
Because then we could do 90 minus 30, because the bold line and the vertical line of y1 equals a right triangle.
Yeah, so how much would this angle be? Yep. So you could either use that angle or you could label the angle down here. It doesn't matter which angle you use. You don't need both of them, but you need one of them. So we could do the 60. If you want to label the other one, that's 30. And then how about in the other triangle? Yeah, and there's a lot of ways to figure it out. If you think of this as two parallel lines with a line cutting through them, if that's a 45, then so is that, just from geometry. Or you can think of it as a 90 and you have a 45, subtract 45, either way. Okay, so now we need to figure out x1, y1, x2, and y2 exactly like we did right here. We figured out x and y based off the hypotenuse, which is the tension, and the angle. So we're going to do this 4 times, but eventually we'll kind of hopefully see a pattern where the horizontal stuff is a certain function and the vertical stuff is another function. All right, so let's start with x1. So we're not really finding x1, we're just coming up with a formula for it. All right, so what trig function could I use? And let's do it from the perspective of that angle. What trig function could I use that would involve x1 and the hypotenuse? Cosine. So it would be cosine of 30 equals what? Well, what's the definition of cosine? Oh, Francisco? What's the definition of cosine? Nope, that's sine. Adjacent over hypotenuse. So what side is adjacent to the 30? X1. And what's the hypotenuse? T1. I labeled it up above. Okay, T1. And now, just get x1 by itself. So what's the formula for x1? T1 cosine 30. Okay, the 4 formulas that we're going to come up with are going to look just like this. A tangent times a sine or a cosine of an angle. So now let's do x2. All right. And let's do it from the perspective of that angle. What trig function would I use? Cosine. Cosine 45 equals x2 over t2. And then solving for x2, t2 cosine 45. Okay, so there's that one. Now we need y1 and y2. It's exactly the same thing again with sine. So let's set up one of them and then see if we could just see the pattern for the other one. So y1, what trig function would we use? Sine of 30 equals y1 over t1. Yep, so y1 equals t1 sine 30. And y2 is going to be t2 sine 45. Yeah. So y2 is t2 sine 45. Okay, now we're at a point where we've done all the physics kind of stuff. The physics stuff was really just thinking about forces left and right equaling each other and forces up and down. And then we started to convert that into a trig problem, okay, with all the right triangles. And now we have expressions for all 4 of those things. So all we have to do now is take the equations we have in blue, fill in the expressions, and then we're going to have a system. And then we just solve it. Okay? We're going to get some decimals because we have some sines and cosines in there. but it's basically going to be equivalent to solving something just like this, except that's going to be a sine or a cosine. So is that, so is that, and so is that. That's it. And one of these is equal to a 1200 on that side, not an 8. Okay? But it's basically just like solving that. All right, so we've got x1 equals x2. So x1 is t1 cosine 30. And what's x2? Yep, t2 cosine 45. So if it's confusing, you could think of that as x times something equals y times something. It's basically like 2x equals 5y. That's basically what you have right there. Two different variables, two different numbers. All right, so that's our first equation. And the second equation is y1. And what comes after that? Plus y2. The force is pulling up. Sine 45. And equals what? Equals 1200. Okay, and that's like x times something plus y times something equals a number. And now we just have to solve it. So two equations, two variables. It might look a little confusing because of all the sines and cosines, but everything that's a sine and cosine is just a number. It's a decimal, but it's just a number. All right, so what would I do first to solve that system?
You could divide by cosine of 30.
Yeah,
Besides to get t1.
so what we could do is solve the top one for t1, or t2, it doesn't matter. So solve it for t1, and what would you get?
T2 cosine 45 over cosine 30.
Cosine 30. That's t2,
Yeah.
t1, sorry. Now what do you do with that?
And then you can plug that in for t1 in the other equation.
Yeah. Plug that in right there. Eventually, we're going to round all these off. I'm just not doing it yet because I want to save the rounding for the last step. So t1, I'm going to change it to t2 cosine 45 over cosine 30. And I'm going to put a times sine 30 in the top because I still have that part I need to write down. Okay, I'm going to round all that off in the next step. Plus t2 sine 45 equals 1200. Okay, so this is the part where we need a calculator. So I'm going to do cosine 45 times the sine of 30. All right, so cosine 45 times sine of 30. And we're going to divide by cosine 30. Okay, so we get 0.408. And what's the sine of 45 as a decimal? .707. All right. What would I do now?
You could combine the
Yeah, they're both like terms, so add them up. So 0.408 plus 0.707, we get 1.115. Yeah, and then divide each side by that. And that'll be the tension in cable 2. Okay, so 1200 divided by 1.115. So there's roughly 1,076 pounds of tension in that cable. All right. And now that I know the tension in cable 2, all I have to do is take that, plug it back in right there for T2, and then I can find T1. Okay, so it's going to be, I'm just rounding it to 1,076 times cosine 45 divided by cosine 30. Okay, so the tension in the other cable is 879 pounds. Is that more than the object weighs, or less, or the same? Yeah, it's more. And that's because the cables are pulling against each other. So what that would mean is if you were to cut one of these cables, the object would probably snap back pretty quickly and towards the cable that was still attached. Okay, so there's definitely, if we look at the whole thing, there's a lot of steps, but it's not, any step individually isn't really that hard. Okay, this concept is the same in every problem. So what we have in blue, you could use that on every problem. Just change the 1200 to whatever the weight is. And then you have to do the trig part 4 times, or just remember, it's always the horizontal component times T1, and that's the cosine. And then it's the vertical component times T2, and that's the sine. And you can just set up those 4 boxes. And then you fill them in. And then from there, it's basically algebra 1. Solve the system. If you don't like the sine and cosines, you could round them off earlier and get decimals. But make sure you go to at least 3 decimal places. But that's exactly how every problem, you'll have one in the homework like that, and you solve it exactly the same way. All you have to do is change 1200 to whatever number they give you. Yeah.
What was the last thing you did to get T1?
I plugged T2 back into our substitution step. And if you're going to do a lot of these problems, you could probably figure out a shortcut. Like, you've got a formula right here to figure out the tension in cable 1 all the time. It's the tension in cable 2 times the cosine of the angle on the right divided by the cosine of the angle on the left. So you could probably come up with a shortcut without having to set these up every time. Just call that the angle on the right, the angle on the left. Okay. And then the cable on the left times the sine of the angle on the left plus the cable on the right times the sine of the angle on the right equals the weight of the object. If you write down exactly what I just said, that gives you a shortcut, filling in what you need to fill in. Okay, so any question on that? It's probably the hardest word problem all week. Ever? Maybe not ever. But maybe for this week. Okay, questions on that? All right, so I think like what we did yesterday, we'll take a look at the start of this section. We probably won't finish it. Okay, and this section deals with what's called the dot product. So this is going to be the first time we've ever multiplied a vector times a vector. We've multiplied a number times a vector, but that just scales it. We've never taken a vector and multiplied it by a vector. What's that? Yep, I'll have to give you the new packet for homework. Just remind me of that. Okay, so what I've done here is I've just written 2 vectors in unit vector form. Each vector has a horizontal component. Each vector has a vertical component. And those would all be numbers. They could be fractions, decimals, positive, negative. But A1, A2, B1, B2 are all numbers. So the dot product, okay? In other words, if you wanted to take V dot W, okay, you can't say times W. You have to say V dot W. All right? To find that product, you take the horizontal components, A1 and A2, multiply them together. Then take the vertical components, B1 and B2, multiply those together, and then add the result. That's how you find a dot product. Yep. Multiply the horizontal components, multiply the vertical components separate, and then add the 2 results. So if you were to do this out, if you do A1 times A2, what kind of thing would your answer be? I asked this question earlier when I said which one of these 4 calculations is different than the rest. That's what I'm looking for here. Yeah, that's a number. What about B1 times B2? And then if you add 2 numbers, you get a number. So the answer when you do a dot product is a number, like 7. It's just a number. And the reason I said you can't say times is because one way to multiply vectors is with a dot product. Another way to multiply vectors is with a cross product. These 2 symbols mean totally different things with vectors. So I said to you, when we studied addition, I said it was commutative. And I said that that property won't always work. It doesn't work here. If you find V cross W, and then you find W cross V, the answers aren't the same. We'll see if the dot product is the same. You could probably figure it out right now whether it is or not. But we'll check it and see does it come out the same. Okay, we're not going to do cross product today. Okay, we're just going to look at dot product. The other reason I can't do cross product is because cross product is a 3D thing. It only works in 3D. Dot product I can do in 2D like we're going to do right now, or 3D. And it's exactly the same in both. Okay, so let's find V dot W. Okay, so doing it in the order I have written, what would be the first 2 things you multiply? 2 and 5. And negative 3 and 3. So 2 and 5 is going to give me 10. And minus 9. So what's the dot product? 1. So eventually, the dot product is going to be part of a formula where that's one of 2 things we have to do, finding the dot product and then finding the magnitude, which you already know how to do. If you know how to find the dot product and the magnitude, you can figure out something special about these 2 vectors, which we'll see in a little bit, maybe. What about doing it this way? W dot V. 5 times 2. Yep. It's always your horizontal components, the W first, then the V. W, then V. And then 3 and negative 3. So what are you going to get? You get 10 minus 9 again, which is 1. So what does that mean about the dot product? It's commutative, yes. Okay, the dot product is commutative. Okay, let's try V dot V. So I'll scroll back up. What would V dot V be? What times what plus what times what? 2 times 2 plus negative 3 times negative 3. Yeah. So 2 times 2, negative 3 times negative 3. And what is 2 times 2? I mean, I don't, not 4, but I'm asking for, yeah, that's what I was getting at. It's 2 squared plus negative 3 squared. And the reason I wrote it like that, and now I'll simplify it, is because I want, hopefully, to notice something. Does anybody notice what that is almost, but not quite? It's almost the magnitude, except you didn't do what? You didn't square root it. So technically, that is the magnitude squared. You didn't square root it. All right. How about W dot W? So it's 5 squared plus 3 squared, which is 36, right? Yeah, 34. So that's the magnitude squared. You didn't take the square root there. And that always happens. If you dot a vector with itself, you get the magnitude of the vector squared. Same thing, w dot w. If you dot a vector with itself, you get the magnitude squared.
That's easy.
Okay? What would that one be? Someone said 0? Can you be more specific? Just want to make sure we understand something here that I've talked about. Is it a vector?
No.
No, it's 0, the number. Right? When you do a dot product, I had asked someone earlier, what do you get? And it's a number plus a number, which is a number. So this is 0. If you wrote this, that would get marked wrong. The answer, when you do a dot product, is not a vector. Any question on that? In the calculation, just 2 times 0 plus 6 times 0, so it's just 0 plus 0. The dot product is distributive. Okay, you can do the distributive property with it. So u dot in parentheses v plus w is like u dot v plus u dot w. It's not something we do a lot, but if it came up in a problem, you can do it. Okay, and the real point of doing the dot product is to help us find something between two vectors. Okay? If I had a vector like this and another one like this, what do you think I could find out about those two vectors? What's something you might want to know about them? Besides their magnitudes, we could find the length of each vector. But the way that I just lined them up, we could also find the what could you find in that diagram? It's something I could ask you to find. Besides the length of each vector. Yeah? Yeah, the angle. I could say, how much is this angle between the two vectors? Now, do we have a way that we could figure that out without me showing you any other information right now? Well, if you had, let's say, something like this. If I said, here's a vector. Here's another vector. Could you figure out that angle? How could you figure it out? If you connected that. And what could you figure out about that triangle if you really wanted to? Something even someone in Algebra 1 should be able to figure out. Yeah, if you have the coordinates for all these vertices, you can find all three sides. And do you remember the kind of triangle we called that? We had it's oblique, and it's specifically, it's a what? It could be scalene. I don't know if two of the sides come out the same, but if you know all the sides, it makes it a 3 letters. Yeah, it's a side-side-side triangle. And is that one of the triangles that we can solve?
Yes.
Yeah, with which law? That's a law of cosines. So, if you knew all 3 sides, which you could find them, use your distance formula, just do it 3 times, you could find any one of these angles. You don't have to do all 3, but you have to find the one that I was asking about, which is right there. So, technically, you don't need anything else to find the angle between 2 vectors. You could do it with what you know right now. But there is a shortcut to finding the angle between 2 vectors. And you might have a guess what the formula is based off of. What do you think the formula is based off of that I just showed you? The what? Okay, that's part of it, but then it uses the three sides in another formula. What? Yeah, it's the law of cosines. So if we were going to derive the formula that I'm about to show you, it has to do with the law of cosines. We're not going to go through the proof of it, but it's a relatively straightforward formula. It's the cosine of the angle equals the dot product over the product of the magnitudes. So the cosine of the angle equals the dot product over the product of the magnitudes. Okay, so we'll finish up with finding a dot product and the product of the magnitudes, which will allow us to find the angle. Okay, so there's three things you have to find. The dot product, the length of the first vector, and then the length of the second. All three things we know how to do. So the dot product here would be, what's 4 times 2? And then negative 3 times 5? So what's the dot product? Negative 7. That's the numerator. And now I need the length of u. Five. It's 16 plus 9. And then take the square root of 25. So that comes out nice. And what's the length of v? Square root of 29. Okay, so now just fill that into your formula. Cosine of your angle equals the dot product over the product of the magnitudes. And now, what are you going to do to get theta by itself? Yeah, do the inverse cosine. So it's inverse cosine of negative 7 divided by 5 square root 29. I probably need to put the 5 square root 29 in parentheses, like that. So it does the denominator first and then divides the numerator by it. So we get 105.07. That's the angle between the two vectors. Okay, any questions on that one? All right, so the homework tonight. Let's go back here for a second. You already did sum of 344 last night. So it's just those 6 or so problems. 7. Okay, that's on the static equilibrium. There's one problem on that, the velocity vector stuff. And there'll be some from the dot product. Probably 1 or 2 from there. Does everybody have this one? Okay. And then for dot product, all right, let's do 7 through 11. Do all on that, 7 through 11. Okay, and the directions ask you to do 3 things. Just do parts A and B. Part C asks if the vectors are parallel or perpendicular. We haven't talked about that. You can probably guess what the angle would be if the vectors were perpendicular, but hold off on that. Just do parts A and B.